In part 2 of our lab exercise, we're going to specifically examine electrochemical cells. When considering electrochemical cells, there are cells known as spontaneous electrochemical cells and also non-spontaneous electrochemical cells. When referring to spontaneous cells go by the name of either voltaic or galvanic cells, whereas electrochemical cells that are non-spontaneous go by the name of electrolytic cells. This would be one means we have of distinguishing between spontaneous electrochemical cells and non-spontaneous electrochemical cells. For our purposes, we're going to focus on the voltaic or galvanic cells in this part of our lab exercise. Let's take a moment and walk through how to diagram and set up and work with a spontaneous electrochemical cell, also known as a galvanic or voltaic electrochemical cell. Our first step will be to identify the possible reduction half reaction that can take place in each cell or each beaker of our setup. For our beaker on the left, the possible reduction half reaction is the nickel 2 plus gaining 2 electrons turning to nickel solid. For the beaker on the right, the possible reduction half reaction is the copper 2 plus gaining 2 electrons and turning into copper solid. We need to find what's our reduction potential for each of these reduction half reactions. Looking on our table of reduction half reactions, we find that for the nickel half reaction, the reduction potential is negative 0.25 volts, whereas for the copper 2 plus, it's a positive 0.34 volts. What this tells us, because the copper reduction potential is more positive, a higher positive value, is that the copper half reaction is more easily reduced than the nickel reaction. Consequently, the copper reaction will stay as our GER, or our reduction half reaction, whereas the nickel reaction, we're going to have to take that and flip it and turn it from a GER into our LEO to make that our oxidation half reaction. Now that we've taken the nickel reaction and flipped it, this half reaction represents our process of oxidation. And because it's now an oxidation, that would mean that we have to take the voltage, our reduction potential, and change this to a positive value for this particular half reaction. The copper 2 plus reaction stays as our reduction, and we now have our two halves. We have both an oxidation half reaction and we have a reduction half reaction to create our spontaneous electrochemical cell. To determine the direction of electron flow in our electrochemical cell, we have to examine where electrons are being lost and where electrons are being gained. In this case, the copper ions are going to be gaining electrons by touching the surface of the copper metal. They pick up electrons and they gain the 2 electrons and turn into elemental copper. Meanwhile, simultaneous to that occurring, in the opposite half reaction, we have the nickel solid losing 2 electrons and turning into aqueous nickel ions. Consequently, the flow of electrons is the electrons leave and flow from where they're being lost, and the electrons flow towards where they're being gained. To label the anode and cathode in our electrochemical cell, we also have to look at where is the location of oxidation and reduction, as these will determine the location of our anode and cathode. The anode is always going to be identified as the location where oxidation takes place, whereas the cathode is always going to be the location where reduction is occurring. So in this electrochemical cell, our anode will be located by the nickel, our cathode will be located at the copper. Now, one means to keep track of which is to focus on the letters that start each one. Over here we see that anode starts with a vowel, as does oxidation. So the vowel-vowel combination always goes together, whereas cathode and reduction, the cathode starts with C, a consonant, as does reduction, and the cathode is always the location of reduction, the anode is always the location of oxidation. To determine our positive and negative electrodes in a spontaneous electrochemical cell, we need to look at the direction of our electron movement. Electrons are negative, and one way to remember this is the negatives are going to flow towards the positive. Consequently, on this side where the electrons are flowing towards the copper solid, this is going to be our positive electrode, and the electrons are leaving, or you could say electrons are getting repelled from, our negative electrode. This would be how we label our negative and positive electrodes in a spontaneous electrochemical cell. As our cell stands right now, we have an incomplete loop for flow of electrons. Currently, our loop is only in the shape of a horseshoe. We need to do something to complete the loop to allow for movement of negative charge between the beakers. What will allow for this to take place is the installation of our salt bridge. Without the salt bridge, we have an incomplete loop and current cannot flow. We need to include a salt bridge to allow for a completion for the flow of negative charge. Now the salt bridge is typically something such as cotton that's been soaked in an aqueous solution with something that contains positive ions such as ammoniums and negative ions such as nitrate. The movement of the negative ions and positive ions in the salt bridge will complete our loop to allow for electrical flow. We've already established that right now our negative flow is in the shape of a horseshoe here. So we can follow the movement of the negative to determine the movement of our nitrate or negative ions in the salt bridge, and that the ions have to go in the direction to continue our loop of negative movement. Consequently, in our setup here, the nitrate or negative ions are going to move into the nickel beaker. Simultaneous to that, the ammonium ions, which are positive, would move in the opposite direction, and the ammonium ions will move into the copper beaker. Another way to determine the movement of ions in the salt bridge is to look at what's occurring in each beaker. In our beaker on the left here, what we have is, as the reaction progresses, the amount of positive nickel ions are going to increase in the solution, increasing the amount of positive present in the water. That would draw the negative nitrate ions into that beaker, which would also complete our movement of negative charge. Meanwhile, in the opposite half reaction, we can see that what's taking place is we have copper ions turning into elemental copper. Consequently, the amount of positive copper is going to decrease in the water in this beaker. Because the amount of positive is decreasing, essentially there's more negative than present in the water, which would draw or pull the positive ammonium ions into the water in that side of the beaker, completing our ion movement in the salt bridge. The next part we have is to determine the movement of the ions within the beakers themselves. What we need to do again in this is examine what's happening in our half reaction. On this side we can see that we have aqueous copper ions that have to gain 2 electrons to turn into elemental copper. To gain electrons, these copper ions have to move towards and touch the surface of the elemental copper. Once touching the surface of the copper ions gain electrons that have flowed over from the nickel, and they turn into elemental copper. We'd actually see the mass of the copper here enlarge as elemental copper forms on the surface. Meanwhile, in the opposite beaker, we'd see that the nickel is turning into aqueous nickel ions. So the positive ions are actually flowing away from the elemental nickel. Over time on this end, we would see the end of the strip actually would start to degrade, and the mass of the strip, the mass of the elemental electrode will actually diminish over time as the solid continues to move off and away from the strip as it turns into aqueous nickel ions. The last thing we have is being able to write the shorthand notation for our electrochemical cell. The shorthand notation follows its LEO, for Leo our lion, goes GER. It's the LEO goes first. Then we have our salt bridge representation. Then we write the GER half reaction. If we look at our LEO oxidation half reaction, we have nickel turning into nickel 2 plus ions. This half reaction, the nickel's written first. There's a little slash, then the nickel 2 plus. We draw our 2 lines to represent the salt bridge. And then we write the half reaction taking place in the GER side which would be copper 2 plus ions turning into elemental copper. We now have our Leo half reaction followed by the GER half reaction, and this would be our shorthand notation for this entire electrochemical cell setup that we have. Our last part now is to take our two half reactions, the half reaction for oxidation, the half reaction for reduction, and combine these two reactions together to get an overall reaction and also determine what's our voltage for this entire reaction. Key thing is we have to make sure the electrons being lost and the electrons being gained are equal in both half reactions to allow the electrons to cancel out when we combine the reactions together. Combining the two half reactions together, we get our overall balanced electrochemical reaction. And when we add our half reaction potentials together, we get a positive 0.59 volts for this particular electrochemical cell. The positive value in here tells us that our reaction is spontaneous. The little degree sign we have here tells us that the conditions here are standard conditions where all of our concentrations would be 1 molar for both reactants and aqueous products. And also, because this came out to be a positive value, not only does it indicate that the reaction is spontaneous, but this reaction would occur, in addition to the products, it would produce 0.59 volts as part of the reaction. So this would be a spontaneous process in which our nickel solid would react with the aqueous copper ions to produce nickel ions, copper solid, and 0.59 volts. Since this is spontaneous, we'd also identify this as being a galvanic or a voltaic cell, which is language that communicates that our electrochemical cell is a spontaneous reaction that occurs and creates some voltage as a new product.